On November 11th, 2025, the Sun unleashed something extraordinary. An X5.1 class solar flare erupted from a region designated AR4274, creating the most powerful electromagnetic explosion Earth had witnessed in over a year. And here's what makes this impossible to ignore. Just 13 days earlier, an interstellar visitor passed through the Sun's domain at its closest approach, carrying plasma and magnetic disturbances from another star system across distances we can barely comprehend. Two cosmic events, separated by less than 2 weeks, one of them originating from beyond our solar neighbourhood. How is that even possible to be mere coincidence? You're watching this because something in you senses that the universe doesn't deal in accidents. When the strongest solar explosion of an entire year occurs within days of an object from interstellar space sweeping past our star, your mind demands answers, and that's exactly what we're here to uncover together, because the implications of what happened in November 2025 might fundamentally change how we understand the relationship between cosmic visitors and solar behaviour. The flare itself was breathtaking in its violence. When AR4274 released that X5.1 explosion, it didn't just send light racing across the solar system, it hurled billions of tons of magnetized plasma into space at speeds exceeding 1,000,000 miles per hour. Radio operators across sunlit regions of Earth suddenly found their signals swallowed by ionospheric chaos. High-frequency communications went dark. GPS systems experienced disruptions. Satellite operators scrambled to protect sensitive electronics from the incoming radiation storm. This wasn't a minor solar hiccup. This was the Sun flexing power we'd almost forgotten it possessed. But here's where your attention needs to sharpen. The timing. October 29th, 2025 marked the perihelion passage of 3I Atlas, the third confirmed interstellar object ever detected by humanity. This comet, born in the space between stars, reached its closest point to our Sun, diving through a region of space where solar magnetic fields writhe and reconnect with devastating energy. Then, just 13 days later, that X5.1 flare erupted. 13 days. In cosmic terms, that's not just close, that's practically simultaneous. Now, before you dismiss this as astronomical coincidence, consider what we're actually discussing. Solar flares happen, yes. They're part of the Sun's natural rhythm, driven by magnetic complexity in active regions. Scientists catalogue them, predict them with varying success, and generally understand the mechanisms involved. But when the most powerful flare of an entire year occurs within such temporal proximity to an interstellar comet's perihelion passage, something in the data starts whispering questions that mainstream solar physics hasn't fully addressed, and those whispers deserve investigation. Think about it this way. You don't question a single raindrop, but when the forecast says clear skies and suddenly a downpour begins exactly when a rare atmospheric phenomenon passes overhead, you start wondering about connections. That's where we are with 3I Atlas and the November 11th flare. The official position is that these events are unrelated, that sunspot AR4274 generated the flare through conventional magnetic reconnection processes independent of any external influence, and that position might be entirely correct. But what if it isn't? What if there's a mechanism we haven't considered? A way that interstellar objects carrying alien magnetic signatures and plasma characteristics could interact with solar dynamics in ways our models don't yet capture. The geomagnetic storm that followed the flare was classified as severe, reaching G4 intensity levels. Auroras blazed across skies far south of their usual territories. Power grid operators activated protocols designed to prevent cascading failures. This wasn't theoretical space weather. This was real-world infrastructure threat, the kind that governments and corporations have spent billions trying to predict and mitigate. And at the heart of this event lies a mystery that conventional explanations haven't fully satisfied. Before we go further, I need you to engage with this investigation actively. If this topic pulls at your curiosity, if you sense that space phenomena hold secrets we're only beginning to grasp, then hit that like button right now. This video represents hundreds of hours of research, timeline analysis, and careful synthesis of scientific data and expert perspectives. That mystery-driven investigation deserves visibility. And more importantly, it builds the community of thinkers who refuse to accept surface-level explanations. When the universe presents anomalies worth examining, the conventional wisdom says comets don't influence solar flares. The Sun is too massive, too energetic, too magnetically dominant for a relatively tiny ball of ice and rock to affect its behaviour. And mathematically, that makes perfect sense. The Sun contains 99.86% of all mass in our solar system. A comet, even an interstellar one travelling at extraordinary velocities, represents negligible gravitational influence, but gravity isn't the only force at play in space. Plasma dynamics, magnetic field interactions, charged particle streams. These phenomena operate by different rules where size doesn't always dictate influence. A match is tiny compared to a forest, but under the right conditions, that match can trigger an inferno. So here's what we're going to do together. We're going to examine the evidence piece by piece, building a case not of certainty but of possibility. We'll explore the timeline with precision, understanding exactly where 3i Atlas was and what the Sun was doing at each crucial moment. We'll dive into the physics of solar flares, demystifying how these explosions occur and what might potentially trigger or amplify them. We'll hear from scientists who work at the cutting edge of solar research, both those who dismiss any connection and those whose curiosity leads them towards speculative questions. And we'll explore theoretical mechanisms, however unlikely, by which an interstellar visitor might interact with solar magnetic architecture. What you're about to experience isn't conspiracy theory. It's legitimate scientific inquiry into an anomaly that deserves attention. The difference is crucial. Conspiracy thinking starts with a conclusion and cherry-picks evidence to support it. Scientific inquiry starts with an observation and follows evidence wherever it leads, even if that destination is simply, "We don't know yet." That's the approach we're taking here, and it requires intellectual honesty, critical thinking, and willingness to sit with uncertainty. The stakes are higher than you might realize. If interstellar objects can influence solar activity, even marginally, then our entire framework for predicting space weather needs revision. We're entering an era where our technological civilization depends increasingly on satellites, GPS navigation, electrical grids, and communication systems, all vulnerable to solar storms. Understanding every possible factor that might affect solar behavior isn't academic curiosity. It's survival intelligence for a species that's betting its infrastructure on space-based systems. Something happened in November 2025 that defied the odds of pure chance. An interstellar comet and the most powerful solar flare of the year occurred in suspicious proximity. Maybe it means nothing. Maybe the universe simply aligned two unrelated events in a way that makes pattern, seeking human minds see connections that don't exist. Or maybe, just maybe, we're witnessing evidence of cosmic interactions that our current models don't fully account for. That's the question driving this investigation, and by the end of this video you'll have every piece of evidence necessary to form your own informed perspective. But first, we need to understand the journey that brought 3i Atlas into the Sun's domain and what made that passage so extraordinary. Let's talk about what it means to be an interstellar traveller. 3i Atlas didn't form in our solar system. It was born somewhere else, in conditions around another star or perhaps in the frozen void between stellar systems, and it's been journeying through the galaxy for time frames our minds struggle to comprehend. This object has seen regions of space we'll never visit, passed through magnetic environments shaped by stars we can't even name, and carried with it the chemical and electromagnetic signatures of cosmic territories foreign to our local neighbourhood. On October 29, 2025, this wanderer reached perihelion, the point of closest approach to our Sun, at approximately 1.36 astronomical units. To put that in perspective, that's about 203 million kilometres from the solar surface, between the orbits of Earth and Mars, but still far from the Sun's immediate corona. At that distance, the comet experienced solar radiation intensity roughly 6 times stronger than Earth receives, enough to vaporize ices and release gases that formed a distinctive coma and tail stretching millions of miles behind its nucleus. But distance tells only part of the story. What matters more is context, the environment through which 3i Atlas travelled during its perihelion passage. The Sun isn't a static ball of glowing gas. It's a dynamic magnetic entity, constantly generating and reshaping field lines that extend far into space, creating what scientists call the heliosphere. This magnetic architecture is strongest near solar active regions, areas where sunspots form and where the energy for solar flares accumulates. during late October 2025, several significant active regions dotted the Sun's visible hemisphere, including the one that would later be designated AR4274. Think about what that means. 3 I-Atlas, carrying plasma and magnetic characteristics potentially shaped by interstellar environments, passed through the inner solar system at a time when solar magnetic fields were already in states of heightened complexity and energy storage. The comet wasn't moving through empty space. It was moving through a magnetically structured medium, and as it did so, it released material: water vapor, carbon dioxide, carbon monoxide, dust particles, all ionized by intense solar radiation into charged plasma that could potentially interact with ambient solar magnetic fields. The trajectory mattered too. 3 I-Atlas didn't pass through the solar system along the ecliptic plane where most planets orbit its path was inclined, carrying it through regions of the heliosphere that experienced different magnetic conditions than the equatorial zones. The comet's velocity was extraordinary, around 68 kilometers per second at perihelion, fast enough to complete its closest pass in a matter of hours rather than days. This wasn't a leisurely orbit. This was a high-speed transit through one of the most magnetically active environments in the solar system. Now here's where timing becomes fascinating. The comet reached perihelion on October 29th. For the next several days, it continued moving away from the Sun but still remained within the inner heliosphere, that region where solar influence dominates, and magnetic field lines connect directly back to the solar surface. Throughout this period, from October 29th through early November, 3 I-Atlas was releasing material, creating a plasma tail that stretched back toward the Sun due to solar wind pressure. This tail, composed of ionized particles stripped from the comet's nucleus, existed as a tenuous but real structure connecting the comet to regions closer to the solar surface. What happened during those days following perihelion? Solar physicists were monitoring several active regions, including AR4274, which was developing the magnetic complexity characteristic of flare-productive sunspots. By November 10th, this region had accumulated significant magnetic energy, storing it in twisted field lines that arced above the Sun's surface. The stage was being set for a major release, the kind of magnetic explosion that produces X-class flares. And then, on November 11th, just 13 days after 3 I-Atlas reached perihelion, AR4274 erupted the X5. One flare represented a release of energy, equivalent to billions of nuclear weapons detonating simultaneously, all packed into a magnetic reconnection event that lasted mere minutes, but ejected plasma that would take days to reach Earth. The question that should haunt anyone paying attention is this: why then? Why did the most powerful flare of 2025 occur during this specific temporal window when an interstellar comet, something that carries cosmic properties unlike anything native to our solar system, was traversing the inner heliosphere? Conventional solar physics attributes the flare entirely to processes within AR4274 itself. The sunspot had been building magnetic stress over days, and eventually that stress exceeded the threshold where magnetic field lines could maintain their configuration. Reconnection occurred, energy released, flare erupted. This explanation requires no external trigger, no special timing, no consideration of anything beyond the Sun's own internal dynamics. It's clean, self-contained, and consistent with decades of solar observation. But consider this alternative perspective, not as fact but as possibility worth examining. What if the comet's passage, specifically the plasma and magnetic disturbances it introduced into the inner heliosphere, created subtle perturbations that propagated sunward? What if those perturbations, too small to cause a flare on their own, acted as a catalyst for a system already on the edge of instability? You don't need to supply all the energy for an explosion if you simply provide the trigger that releases energy already stored. That's the essence of catalytic influence, and it's how many systems in nature operate when multiple factors converge. The distances involved seem to argue against any connection. By November 11th, 3 I-Atlas was much farther from the Sun than it had been at perihelion, perhaps 0.8 to 0.9 astronomical units, and increasing. Could something that far away influence solar surface dynamics? In a gravitationally dominated system, absolutely not. But the heliosphere isn't governed only by gravity. It's a magnetically connected environment, where disturbances can propagate along field lines at speeds approaching that of light. If the comet's plasma tail or associated magnetic signatures created perturbations during perihelion passage, those disturbances could theoretically propagate back toward the Sun and arrive days later, coincident with the timing of the November 11th flare. This is speculation, yes, but it's grounded speculation, the kind that asks whether our understanding of solar system dynamics is complete, or whether phenomena like interstellar comets might introduce variables we haven't fully integrated into our models. The comet's solar dance ended without definitive answers, leaving behind a trail of data and a timing coincidence that refuses to quietly fade into astronomical history. To understand whether there's any merit to this line of inquiry, we need to dive deep into the fundamental physics that govern solar flares themselves, examining how these explosions occur and what factors might influence their timing and intensity. Let's strip away the mystery and understand what actually happens when the Sun explodes. A solar flare isn't magic, and it isn't random. It's a consequence of magnetic field lines becoming so stressed, so twisted, so energetically overloaded that they can no longer maintain their structure. When that threshold is crossed, something spectacular occurs. The field lines snap, reconnect in new configurations, and in that violent rearrangement, they convert magnetic energy into heat, kinetic energy, and electromagnetic radiation across the entire spectrum from radio waves to gamma rays. Think of it like a rubber band stretched to its limit. The more you twist and pull it, the more potential energy you store in that elastic material. Eventually, if you keep adding stress, the rubber band either snaps or releases suddenly, converting all that stored potential into kinetic motion in an instant. Solar magnetic fields work similarly, except instead of rubber, you're dealing with plasma, the fourth state of matter where atoms are stripped of electrons and exist as a soup of charged particles that respond to magnetic forces. The Sun generates these magnetic fields through a process called the dynamo effect. Deep in the solar interior, differential rotation, where equatorial regions spin faster than polar regions, stretches and twists magnetic field lines. Convective motions, like boiling water but on a stellar scale, further tangle these fields. Over time, loops of magnetic field emerge through the Sun's visible surface, the photosphere, creating the dark spots we call sunspots. These spots appear dark not because they're cold in absolute terms, but because they're cooler than surrounding areas, roughly 4,000 degrees Celsius compared to the 5,500 degrees of the rest of the photosphere. That cooling happens because magnetic fields inhibit convection, preventing hot material from below from reaching the surface. But those magnetic loops extending above the photosphere into the Sun's atmosphere, the corona, are where the real action occurs. The corona is extraordinarily hot, millions of degrees compared to the photosphere's thousands, a temperature inversion that scientists still don't fully understand. Within this superheated environment, magnetic field lines arch high above active regions, sometimes stretching hundreds of thousands of kilometers into space. And as the photosphere below continues to churn and rotate differentially, those field lines get twisted further, storing increasing amounts of magnetic energy. Eventually, the system becomes unstable. Adjacent magnetic loops with opposite polarity drift close enough that they interact, or a single loop becomes so twisted that it can't hold its shape. When this happens, magnetic reconnection occurs. This is the key process that powers solar flares. Opposing magnetic field lines meet, break, and reconnect in different configurations, like cutting and splicing wires to create a new circuit. But this isn't a gentle rearrangement. It's explosive. The magnetic energy stored in those stressed field lines converts almost instantaneously into other forms of energy. Particles, mainly electrons and protons, are accelerated to significant fractions of light speed. These energetic particles slam into the denser plasma below, heating it to tens of millions of degrees. That superheated plasma emits intense radiation across the electromagnetic spectrum X-rays, an extreme ultraviolet radiation blast outward at light speed, reaching Earth in about 8 minutes. Radio bursts follow, causing the shortwave blackouts that operators experienced during the November 11th event. And often, though not always, a coronal mass ejection follows, where billions of tons of plasma are hurled into space carrying magnetic fields with them. The X5.1 flare from AR 4274 on November 11th, 2025, represented the high end of this energy spectrum. X-class flares are the most powerful classification, and the number following the X indicates relative strength within that class. An X5 flare releases energy equivalent to about 1/10 of all the energy the Sun emits in an entire second, which might not sound impressive until you realize the Sun's total output powers every planet, moon, asteroid, and comet in the solar system with energy to spare. Concentrating that much energy into a localized explosion lasting minutes produces effects that ripple throughout the heliosphere. What made this particular flare the strongest of 2025? Timing and magnetic configuration in AR 4274. The sunspot complex had developed what's called a beta-gamma-delta magnetic configuration, one of the most flare-productive arrangements possible. In this setup, positive and negative magnetic polarities are intermixed in complex patterns, with strong gradients where opposing fields come into close proximity. It's the solar equivalent of storing gunpowder and sparks in the same container. The only question isn't if an explosion will occur, but when. Solar physicists use sophisticated instruments to measure these magnetic configurations. Heliosismology lets them peer below the surface, detecting subsurface flows and magnetic structures before they emerge. Magnetograms map field strengths and polarities across the solar surface. Extreme ultraviolet telescopes reveal the coronal loops and their evolution over time. All this data feeds into models attempting to predict when a region will produce a flare and how powerful that flare might be. But prediction remains maddeningly difficult because the triggering mechanisms, those final factors that push a system from unstable to erupting, aren't fully understood. This is where the 3i Atlas question becomes genuinely interesting from a physics standpoint. If magnetic reconnection in AR 4274 was inevitable given the region's configuration, then the comet's presence is irrelevant, a temporal coincidence with no causal relationship. But if the timing of reconnection can be influenced by external factors, by perturbations in the surrounding corona or heliosphere that nudge an already unstable system over the edge, then suddenly an interstellar comet passing through during the precise window of maximum instability becomes a variable worth investigating. Think about avalanches. Snow accumulates on a mountainside layer after layer, building stress and potential energy. The avalanche is inevitable in a sense. The slope can't hold infinite snow, but what determines when it releases? Sometimes it's additional snowfall, sometimes it's warming temperatures, sometimes it's a seismic tremor, sometimes it's sound waves from a jet passing overhead, or even a skier traversing the slope. The trigger can be small relative to the energy released because it's not supplying the energy, it's merely providing the perturbation that initiates the release of energy already stored. Could 3i Atlas have acted as such a trigger? Under conventional understanding, no. The distances involved, the weakness of any potential interaction, the self-contained nature of solar magnetic dynamics, all argue against it. But conventional understanding has been revised before when new phenomena revealed gaps in existing models. Magnetic reconnection itself wasn't fully understood until the space age gave us instruments capable of observing it directly. Coronal heating remains partially mysterious. The solar dynamo's precise mechanism still generates scientific debate. The November 11th flare sent a wave of electromagnetic radiation across the solar system, followed hours later by a massive plasma cloud, the coronal mass ejection. When that CME reached Earth on November 13th, it compressed our magnetosphere, triggering the G4 geomagnetic storm that produced widespread auroras and infrastructure concerns. This wasn't abstract physics, it was real-world impact, the kind that reminds us how dependent our technology has become on space weather conditions, and if there's even a remote possibility that interstellar objects can influence the timing or intensity of such events, then investigating that possibility isn't optional, it's essential. The physics of solar flares provides the foundation for understanding what happened on November 11th. But physics alone doesn't explain timing. For that, we need to turn our attention to the timeline itself, examining with precision where 3i Atlas was, what the Sun was doing, and whether the temporal relationship between these events suggests anything beyond coincidence. That timeline analysis reveals patterns that conventional explanations struggle to dismiss entirely. Now we're going to slow down and examine the evidence like investigators at a crime scene, because timelines don't lie. They might not tell us everything, but they establish what happened when, and sometimes those patterns reveal connections that narrative explanations miss. So let's build this chronology piece by piece. focusing on the crucial window between late October and mid-November 2025. October 29, 2025, 0 hour 3. I-Atlas reaches perihelion at approximately 1.36 astronomical units from the Sun. At this moment, the comet is subjected to solar radiation intensity more than twice what Earth experiences. Its nucleus, composed of ices formed in interstellar conditions possibly millions or even billions of years ago, begins shedding material at maximum rate. Water vapor, carbon dioxide, carbon monoxide, organic compounds, dust, all of it streaming away from the nucleus, ionized by solar ultraviolet radiation into a glowing plasma that forms both the coma surrounding the nucleus and the twin tails, dust tail and ion tail that extend millions of miles anti-sunward. The ion tail deserves special attention. Unlike the dust tail, which follows a curved path due to orbital mechanics, the ion tail points directly away from the Sun because it's composed of charged particles pushed by solar wind. This tail is essentially a stream of plasma, a conducting medium that can carry electric currents and respond to magnetic fields. At perihelion, 3I Atlas's ion tail stretched back toward the outer solar system, but the base of that tail, where it connected to the coma and by extension to the heliospheric environment closer to the Sun, existed within regions where solar magnetic fields maintain coherent structure. October 3031, 2025. The comet continues its high-speed exit from the inner solar system, but it's still close enough that solar influences dominate its behavior. Material continues streaming from the nucleus, fed by heat, absorbed during perihelion passage. The coma remains large and active. Meanwhile, on the Sun's surface, multiple active regions are being monitored, including the developing complex that will become AR4274. At this point, the region shows magnetic complexity, but hasn't yet reached the critical configuration that produces major flares. November 15th, 2025, 3I Atlas moves farther from the Sun each day, decreasing in brightness as distance reduces solar heating, but the plasma tail persists, growing longer as it stretches back through space the comet has already traversed. By early November, the comet is roughly 0.7 to 0.75 astronomical units from the Sun, about 65 to 70 million miles. That seems far too far for direct influence on solar surface dynamics. But remember, magnetic field lines in the heliosphere don't respect distance in the way gravitational effects do. They create connectivity across vast spatial scales. During this same period, AR4274 evolves. Magnetic flux continues emerging through the photosphere, building the complexity that characterizes flare-productive regions. Solar physicists monitoring the region note the beta-gamma-delta configuration developing, the hallmark of high flare risk. But development alone doesn't guarantee timing. The region could maintain this configuration for days without producing a major flare, or it could erupt multiple times in rapid succession. The triggering mechanism remains elusive. November 6-10, 2025. The comet is now well past 0.8 astronomical units. Fading from the view of all but dedicated observers with appropriate telescopes, its scientific interest begins to wane as it exits the most active phase of its solar encounter. But on the Sun, AR4274 reaches peak complexity. The magnetic stress building in this region is palpable to those who know how to read magnetograms and coronal imagery. Energy continues accumulating, stored in twisted field lines arching high above the photosphere. It's a powder keg awaiting ignition. November 11th, 2025 at approximately 2:01 UTC. AR4274 erupts. The X5.1 flare explodes across multiple wavelengths simultaneously. Extreme ultraviolet radiation surges, captured by solar monitoring satellites. X-ray flux spikes to levels representing the strongest solar event of the entire year. Radio telescopes on Earth detect the characteristic burst patterns indicating energetic particles accelerating to relativistic speeds. Minutes later, chronographs observe the associated coronal mass ejection, lifting off from the same region, a massive plasma cloud carrying billions of tons of solar material and embedded magnetic fields into space on a trajectory that will intersect Earth's orbit 13 days. That's the temporal gap between 3I Atlas reaching perihelion and the most powerful solar flare of 2025, erupting from AR4274. 13 days during which the comet transited from maximum solar proximity to well beyond the Earth-Sun distance, and during which AR4274 evolved from developing complexity to explosive release. Is 13 days enough time for any physical connection between these events? That depends entirely on the mechanism you're considering. If you're thinking gravitational influence, the answer is unequivocally no. 13 days, 13 hours, or 13 seconds wouldn't matter because gravitational effects propagate at light speed and operate continuously. There's no delay mechanism that would separate a comet's perihelion passage from a gravitational response by 13 days. But gravity isn't the only game in space physics. Consider instead electromagnetic and plasma effects. When 3I Atlas passed perihelion on October 29th, it was actively dumping ionized material into the heliosphere. That material, charged and subject to electromagnetic forces, would interact with solar wind and the ambient magnetic field structure. Depending on conditions, those interactions could generate waves, perturbations in magnetic field strength or orientation, that propagate through the heliosphere. These perturbations wouldn't travel instantaneously. They'd move at speeds determined by the properties of the medium, potentially taking days to propagate from the comet's location. Back toward the Sun, magnetohydrodynamic waves, for instance, are disturbances in magnetized plasma that can carry energy and information across vast distances. They travel at speeds related to the Alfvén speed, which depends on magnetic field strength and plasma density. In the inner heliosphere, these speeds can range from tens to hundreds of kilometers per second. If we assume an average propagation speed of, say, 300 kilometers per second, a wave could travel from 1.36 astronomical units sunward over the course of days, arriving in regions closer to the solar surface roughly a week to 10 days after being generated. But here's where the timeline gets genuinely fascinating. The flare didn't occur 7 or 8 days after perihelion. It occurred 13 days after. If we're looking for a direct wave propagation mechanism, the timing seems off unless the propagation speed was slower than typical values, or unless there was a delay between when perturbations reached the inner heliosphere and when they actually influenced AR4274's evolution. Or most likely there's no connection at all and we're seeing pattern where none exists. Yet the pattern persists in the data. Run the numbers yourself if you have access to ephemeris data and solar activity records. October 29th, perihelion. November 11th, X5.1 flare. 13 days. No other X5 class or stronger flare occurred in 2025, making this the standout event of the year, and it occurred within a window where an interstellar comet, an object that by definition carries properties from outside our solar environment, was actively influencing local heliospheric conditions. Now layer in another timeline consideration. AR4274 didn't appear suddenly on November 11th. It was developing over many days prior, visible to solar observers throughout early November as it rotated across the Earth-facing solar disk. The magnetic complexity was building during the exact period when 3I Atlas was between 0.7 and 0.9 astronomical units still within the inner heliosphere, still potentially connected via magnetic field lines to regions closer to the Sun. If there's a mechanism by which the comet influenced solar dynamics, it wouldn't necessarily be through a single pulse or wave arriving at a specific time. It could be through sustained perturbations, subtle modifications to coronal conditions that accumulated over days, and pushed an already unstable system past its threshold slightly sooner than it might have otherwise erupted. The counterargument is straightforward. Correlation doesn't equal causation. Just because two events occur in temporal proximity doesn't mean one caused the other. The Sun produces numerous flares over any solar cycle, and comets, both interstellar and Oort cloud natives, pass through the inner system regularly. Eventually, by pure statistics, a major flare and a cometary perihelion will coincide closely in time. That coincidence, even if rare, doesn't imply physical connection. This argument has merit. Science demands rigor precisely because human brains excel at finding patterns even in random noise. Our ancestors survived because they could detect predator shapes in ambiguous shadows, but that same pattern recognition instinct can lead us astray when analysing complex data. The burden of proof for claiming a comet influenced a solar flare rests heavily on anyone making that claim, requiring not just temporal correlation, but demonstrated physical mechanism and ideally reproducible observations. And yet, even within rigorous scientific frameworks, anomalies drive progress. When observations don't quite fit existing models, when timing seems too precise to dismiss comfortably, that's when deeper investigation is warranted. The timeline connecting. 3i Atlas and the November 11th flare might be coincidence, but it might also be a clue, a data point suggesting that interstellar objects with their foreign magnetic and plasma properties interact with our solar environment in ways we haven't fully characterized. The only way to know is to examine expert perspectives, hearing from those who study these phenomena professionally and understand both the possibilities and the limitations of current models. Science doesn't advance through individual voices claiming truth. It advances through communities of experts examining evidence, debating interpretations, and gradually building consensus around explanations that withstand scrutiny. So what do the experts say about the possibility of 3i Atlas influencing the November 11th solar flare? The short answer is, most dismiss it entirely. The longer answer reveals interesting nuances worth examining. The mainstream position among solar physicists is unambiguous. Solar flares result from processes internal to the Sun's magnetic field dynamics. Active regions like AR4-274 develop through well-understood mechanisms involving differential rotation, convective flows, and magnetic flux emergence. When these regions reach critical instability, magnetic reconnection occurs, releasing stored energy as flares and coronal mass ejections. No external trigger is required, and certainly not from an object as small and distant as a comet, even an interstellar one. Dr. Thomas Berger, former director of the Space Weather Prediction Center and an authority on solar dynamics, has stated in various contexts that comets lack the mass, energy, and proximity to influence solar magnetic field behavior. The Sun's magnetic energy dwarfs anything a comet could contribute by many orders of magnitude. It's like suggesting a mosquito could alter a hurricane's trajectory by flapping its wings harder. The scale mismatch makes the proposition physically implausible. This perspective carries significant weight because it's grounded in decades of solar observation and modelling. We've observed thousands of solar flares. We've tracked their development from magnetic emergence through eruption. We've built sophisticated magnetohydrodynamic simulations that reproduce observed flare behavior, using only solar parameters, no external objects required. The models work. They predict flare probability with reasonable accuracy based entirely on magnetic configuration and energy storage. Adding cometary variables doesn't improve these models because cometary effects, if they exist at all, are below the threshold of detectability. But science also thrives on the edges, where curious minds ask uncomfortable questions. Dr. Angelos Voulidis, a solar physicist at Johns Hopkins Applied Physics Laboratory who specializes in coronal mass ejections and heliospheric dynamics, has noted in published research that the heliosphere is more interconnected than early models suggested. Magnetic field lines create pathways along which disturbances can propagate over vast distances. While he doesn't endorse the idea that comets trigger flares, his work acknowledges that heliospheric conditions can modulate solar wind structure and potentially affect how eruptions evolve once they occur. This distinction is crucial. Modulation versus triggering. Could heliospheric perturbations, potentially including those from cometary plasma tails, affect the fine details of how a coronal mass ejection propagates? Possibly, though evidence is limited. Could such perturbations actually trigger magnetic reconnection in an active region? The consensus says no, but the consensus also acknowledges that our understanding of triggering mechanisms remains incomplete. In private conversations and conference discussions, a minority of solar researchers express openness to exploring non-traditional factors. These aren't fringe figures, they're credentialed scientists with publication records and institutional affiliations, but they're careful to frame their curiosity as speculation rather than assertion. They point to historical instances where solar activity seemed to correlate with unexpected factors, though none of those correlations have survived rigorous statistical testing. They acknowledge the possibility that complex systems like the Sun might respond to influences we haven't fully mapped. But they also emphasize that curiosity isn't evidence, and speculation without testable predictions contributes little to actual scientific understanding. Dr. Melissa McGrath, a planetary scientist with expertise in cometary plasma interactions, offers a perspective from the comet side of the equation. Comets absolutely do create localized heliospheric disturbances. Their plasma tails interact with solar wind, sometimes creating bow shocks and magnetotail structures analogous to planetary magnetospheres. These interactions can be detected by spacecraft and contribute to our understanding of plasma physics. But, Dr. McGrath emphasizes, these effects are localized to the comet's immediate vicinity, typically within a few comet radii. The idea that such localized disturbances could propagate back to the Sun and affect surface dynamics lacks both theoretical framework and observational support. Yet she also notes something intriguing. Interstellar comets are different. They carry volatiles and plasma characteristics shaped by environments unlike our solar system. 3I Atlas, originating beyond our Sun's influence, might have magnetic or chemical signatures that interact with solar wind differently than native comets. This doesn't mean it can trigger solar flares, but it does mean we should study these objects carefully because they provide natural laboratories for understanding how different stellar environments produce different cometary populations. The absence of claimed causation is notable. No published peer-reviewed paper connects 3I Atlas to the November 11th flare. No official statement from NASA, NOAA, or any space weather agency suggests the comet played any role. The scientific consensus, to the extent one exists on this specific question, is that the temporal proximity is coincidental, and this consensus deserves respect because it's built on expertise, observation, and mathematical modelling. But consensus also evolves. There was consensus that continents didn't move until plate tectonics revolutionized geology. There was consensus that ulcers were caused by stress until bacteria were discovered as the culprit. There was consensus that exoplanets were rare until detection methods improved and revealed them orbiting most stars. Scientific consensus represents our best current understanding, not immutable truth. So where does that leave us with 3I Atlas and the November 11th flare? In a space of acknowledged uncertainty, the experts provide no support for a causal connection based on known physics, but they also acknowledge that edge cases, unusual coincidences, and unexplored parameter spaces sometimes hide phenomena that later become integrated into mainstream understanding. The timeline remains suggestive even if not conclusive, and the question of whether interstellar objects could, under any circumstances, influence solar behavior remains open because we've only detected 3 such objects total, and our observation baseline is measured in years, not decades or centuries. What the experts do agree on is this. If there's a mechanism by which comets affect solar flares, it would need to be demonstrated through multiple observations, statistical analysis showing correlation beyond chance, and a physically plausible pathway for influence that withstands mathematical scrutiny. One temporal coincidence, however intriguing, doesn't meet that standard. But one temporal coincidence might justify looking more carefully when the next interstellar object passes through, collecting more detailed data and testing whether the timing relationship repeats or disappears into statistical noise. The expert perspective, then, is both reassuring and unsatisfying. Reassuring because the scientific community isn't claiming wild causation based on insufficient evidence. Unsatisfying because the question remains unanswered in any definitive sense, leaving room for continued speculation and investigation. If we want to move beyond expert opinion into the realm of theoretical possibility, we need to ask a more fundamental question. Even if it's unlikely, what would the mechanism look like? How could an interstellar comet in principle influence solar dynamics? Let's venture into hypothetical territory, not to assert truth but to explore possibility. If an interstellar comet could influence solar flare timing even marginally, what would that mechanism look like? This isn't about proving anything. It's about exercising scientific imagination within the constraints of known physics to see whether any plausible pathway exists. Start with what we know comets release material, primarily water ice, but also carbon dioxide, carbon monoxide, methane, and various organic compounds. Near the Sun, solar radiation ionizes these volatiles into plasma. That plasma forms a coma around the nucleus and gets swept into a tail by solar wind pressure. The ion tail, in particular, is a conducting medium, capable of carrying electric currents and interacting with magnetic fields. Now, the Sun's corona and inner heliosphere are permeated by magnetic field lines. These field lines connect back to the photosphere, where their footpoints anchor in regions of opposite magnetic polarity. Disturbances propagating along these field lines can affect coronal conditions, potentially including the stability of magnetic configurations in active regions. This is established physics. Coronal waves triggered by flares in one region can induce sympathetic eruptions in other regions by disturbing their magnetic structure. The question is whether something external, like cometary plasma, could create similar disturbances. Consider a mechanism involving magnetohydrodynamic waves. When 3I Atlas passed perihelion, its plasma tail extended millions of miles anti-sunward. At the interface between this tail and the solar wind, interactions occurred. The comet's plasma, moving at its orbital velocity, encountered solar wind moving at hundreds of kilometers per second. This velocity shear creates instabilities, potentially generating waves in the ambient magnetic field. These waves could propagate along field lines, travelling both away from and toward the Sun. Now here's where speculation deepens. If waves generated near the comet's perihelion location propagated sunward along favourable field lines, they could potentially reach the inner corona where AR4274's magnetic loops extended into space. Would such waves have sufficient energy to trigger reconnection in an already unstable active region? Almost certainly not if the region was far from instability. But if the region was poised on the edge, storing maximum energy before inevitable release, even a small perturbation might advance the timing of that release. Think of it as the last straw breaking the camel's back. The camel was already carrying near maximum load. The straw didn't supply the energy that broke the camel's back. It simply provided the final increment that exceeded capacity. Could cometary waves serve as that final increment for an active region about to flare? It's not impossible in principle, though the energy budget calculations suggest the comet's contribution would be infinitesimally small compared to the energy already stored in AR4274. Another hypothetical mechanism involves electric currents. The heliosphere isn't electrically neutral. Solar wind carries magnetic fields and electric fields, creating a complex electromagnetic environment. Comets moving through this environment can act like moving conductors, potentially generating localized electric fields and currents. If these currents couple into the larger heliospheric current system, they could theoretically affect current flows along field lines that eventually connect active regions. This mechanism faces enormous scaling problems. The currents generated by a comet are minuscule compared to the massive current systems driven by solar rotation and convection. It's like trying to affect the Atlantic Gulf Stream by adding a garden hose of water. The contribution is real but negligibly small. Yet complex systems sometimes exhibit threshold behavior, where tiny inputs can have disproportionate effects if they occur at precisely the right moment, in precisely the right location. A third possibility involves the comet's magnetic properties. If 3I Atlas carried remnant magnetic fields from its formation environment, fields shaped by conditions around another star or in interstellar space, those fields could differ in orientation or strength from typical heliospheric fields. When the comet passed through the inner heliosphere, these foreign fields would interact with solar fields, potentially creating localized reconnection events or current sheets at the interface. Could information from these localized events propagate back to the Sun? In principle, magnetic reconnection can accelerate particles and generate waves, so it's not entirely implausible that heliospheric reconnection events could send signals sunward. But again, the energy and scale considerations argue powerfully against significance. Localized reconnection events in the heliosphere occur constantly due to turbulence in solar wind. They don't trigger solar flares because they lack the connectivity and energy transfer pathways necessary to affect processes occurring in the dense high magnetic field environment of the solar corona and photosphere. Perhaps the most physically defensible speculative mechanism involves resonance. Complex oscillating systems can respond disproportionately to periodic forcing if the forcing frequency matches a natural resonance frequency of the system. Could cometary perturbations somehow match a resonance frequency of magnetic oscillations in AR4274? This seems far-fetched because the comet's passage was a transient one-time event, not a periodic forcing. But if the comet's plasma wake created oscillations that persisted for days, and if those oscillations happened to match eigenmodes of the active region's magnetic structure, resonant amplification could theoretically occur. I want to emphasize that none of these mechanisms have observational support in the context of solar flares. They're thought experiments, explorations of parameter space where we ask what-if questions to see if physics permits certain interactions. The consensus answer from experts who've worked through the math is that permitted doesn't mean probable, and certainly doesn't mean likely. The energies involved, the distances, the weakness of coupling between cometary and solar phenomena, all of these factors conspire to make cometary influence on solar flares extraordinarily unlikely. Yet extraordinarily unlikely isn't the same as impossible. And in a universe that has surprised us repeatedly with emergent phenomena arising from complex interactions, maintaining openness to unlikely possibilities isn't anti-scientific. It's how we've discovered some of our most interesting physics, by investigating anomalies that didn't fit comfortable explanations and turned out to reveal new phenomena. The theoretical exploration leaves us where we started, with no compelling mechanism but also no absolute prohibition. The laws of physics don't forbid comets from affecting solar dynamics, they just make it improbable, given current understanding of typical parameter values and interaction strengths. If future observations reveal multiple instances of temporal correlation between interstellar cometary passages and solar flares, that statistical pattern would demand theoretical attention, driving physicists to examine these speculative mechanisms more rigorously. For now, though, the theoretical landscape offers possibilities without probabilities, thought experiments without conclusions, and that's actually appropriate for a question this far outside mainstream investigation. What matters more than theoretical speculation is recognizing why this question has practical importance, why understanding every potential factor affecting solar flares isn't academic curiosity, but survival imperative for an increasingly space-dependent civilization. That's where we turn our attention next. Let's shift focus from whether the connection exists to why it would matter if it did. Because here's the uncomfortable truth. Our technological civilization has become exquisitely vulnerable to solar storms, and that vulnerability grows every year as we deploy more satellites, extend more power grids, and depend more completely on GPS navigation and wireless communications. Understanding what triggers solar flares isn't abstract science. It's infrastructure security for a planet that's betting everything on technologies solar storms can destroy. The November 11th, 2025 flare and its associated geomagnetic storm provided a reminder of this vulnerability. The X5.1 flare itself, arriving at light speed, ionized Earth's upper atmosphere, creating a radio blackout across the sunlit hemisphere. High-frequency communications used by aviation, maritime operations, and emergency services went silent. GPS signals, which depend on accurate timing of radio waves traveling from satellites to receivers, experienced degradation as the ionosphere's electron density fluctuated unpredictably. These effects lasted for hours, creating operational challenges for systems that assume reliable communication and navigation, but that was just the immediate impact. The coronal mass ejection that followed the flare carried billions of tons of magnetized plasma toward Earth. When this CME arrived on November 13th, it compressed Earth's magnetosphere, triggering a severe G4 geomagnetic storm. During such storms, the magnetosphere acts like a giant electrical generator, inducing currents in any long conductor on Earth's surface power transmission lines, thousands of miles of wire carrying electricity from generation plants to cities, become conduits for geomagnetically induced currents that can saturate transformers, damage equipment, and even trigger cascading grid failures. The 1989 Quebec blackout remains the canonical example. A geomagnetic storm less severe than the November 2025 event induced currents that tripped protective systems and collapsed Quebec's power grid in 90 seconds, leaving 6 million people without electricity for 9 hours in freezing temperatures. Transformers damaged in that event took months to replace. Now multiply that vulnerability by the expansion of interconnected grids worldwide, the aging of infrastructure, and the increased dependence on electricity for everything from heating to communications to water distribution. A truly severe space weather event, stronger than November 2025, stronger even than the 1989 storm, could potentially cause multi-regional blackouts lasting weeks or months. Satellites face different but equally serious threats. The enhanced radiation environment during solar storms can damage electronics, degrade solar panels, and even cause complete satellite failure. The increased atmospheric drag from upper atmosphere heating during geomagnetic storms can alter satellite orbits, requiring corrective maneuvers that consume limited fuel. SpaceX reported losing 40 Starlink satellites to atmospheric drag during a moderate geomagnetic storm in February 2022. A storm like November 2025's G4 event affects hundreds or thousands of satellites, creating coordination challenges and potential cascade failures If debris from damaged satellites threatens others, airlines reroute polar flights during severe space weather because enhanced radiation at high latitudes poses health risks to crew and passengers. Astronauts on the International Space Station or future lunar bases face acute radiation exposure during solar particle events. GPS-guided precision agriculture, autonomous vehicles, financial transactions time-stamped with GPS clocks, all of these modern systems assume reliable navigation signals that solar storms disrupt. This is why predicting solar flares matters desperately. If we can forecast a major eruption with even 24 hours of warning, operators can take protective measures. Power grid managers can rebalance loads, take vulnerable transformers offline, and stage repair equipment. Satellite operators can place spacecraft in safe modes, orienting solar panels and antennas to minimize damage. Airlines can reroute flights. The economic value of accurate space weather forecasting is measured in billions of dollars of prevented damage and avoided disruption. But our forecasting ability remains frustratingly limited. We can identify high-risk active regions with reasonable accuracy by monitoring their magnetic configuration. We can say, this region has a 40% chance of producing an X-class flare in the next 24 hours, but we can't predict with certainty when a specific flare will occur, how powerful it will be, or whether it will produce a dangerous coronal mass ejection aimed at Earth. The triggering mechanisms, those final factors that push an unstable region from potential to eruption, remain partially hidden behind the complexity of solar magnetohydrodynamics. Now imagine if interstellar comets could influence flare timing. That would add an entirely new variable to prediction models, a factor we'd need to track and integrate into forecasting algorithms. Every time an interstellar object approached the Sun, we'd need to assess its trajectory, composition, plasma output, and potential interaction with solar magnetic fields. The uncertainty in our predictions might increase, or conversely, if we understood the mechanism well enough, the additional information might actually improve predictions by identifying timing factors we currently ignore. But even if the 3i Atlas connection proves coincidental, the November 2025 event highlights a broader truth. We're entering an era where space weather monitoring cannot be optional. Solar Cycle 25, currently approaching its maximum phase, is producing active regions with complex magnetic configurations like AR4274. The probability of major flares and severe geomagnetic storms is elevated, and will remain so for the next year or two. We're overdue for a Carrington-class event, an extreme geomagnetic storm like the one that struck Earth in 1859, producing auroras visible in tropical latitudes and inducing currents strong enough to shock telegraph operators and set paper ablaze. If a Carrington-class storm hit today, studies suggest the economic damage could exceed $2 trillion in the United States alone. With recovery taking years, critical infrastructure would fail. Supply chains would collapse. The financial system, dependent on GPS-timed transactions and electronic communications, would experience catastrophic disruption. This isn't science fiction. It's risk assessment based on known physics and documented vulnerability studies. So whether or not 3i Atlas influenced the November 11th flare, the event serves as a wake-up call. We need better solar monitoring, more satellites observing the Sun from multiple angles, improved models incorporating every factor that might affect magnetic reconnection timing. We need hardened infrastructure, transformers designed to withstand geomagnetically induced currents, satellite systems with redundancy and radiation tolerance. We need public awareness, because when the next severe space weather event strikes, decisions made in minutes could determine whether disruptions last hours or months. The stakes extend beyond Earth, too. As humanity contemplates returning to the Moon and eventually reaching Mars, space weather becomes a survival issue for astronauts beyond Earth's protective magnetosphere. Understanding solar eruption mechanisms, improving prediction accuracy, and learning how to anticipate the most dangerous events will determine whether deep space exploration succeeds or falters under the unrelenting radiation hazards of the heliosphere. This is why investigating anomalies like the 3i Atlas timing matters. Not because we expect comets to be major drivers of solar activity, but because comprehensive understanding requires examining every possibility, closing every knowledge gap, and building models that account for all variables that could conceivably affect the phenomena we're trying to predict. The universe is under no obligation to make prediction easy for us. It's complex, interconnected, and full of subtle influences we're still mapping. Our job is to keep questioning, keep investigating, and keep building better understanding, because the cost of ignorance rises with every satellite we launch and every city that depends on a vulnerable power grid. So where does this investigation leave us? What can we say with confidence, and what remains speculation hovering in the space between evidence and imagination? Let's inventory what we've established and what questions still hang unanswered in the data. We know with absolute certainty that on October 29th, 2025, the interstellar comet 3I Atlas reached perihelion at 1.36 astronomical units from the Sun, passing through the inner heliosphere during a period of elevated solar activity. We know that 13 days later, on November 11th, 2025, active region AR4274 produced an X 5.1 class solar flare, the strongest solar eruption of the entire year. We know this flare triggered a severe G4 geomagnetic storm when its associated coronal mass ejection reached Earth on November 13th. These are observational facts, recorded by instruments, documented in scientific databases, beyond dispute. We know the physical mechanisms that drive solar flares. Magnetic reconnection in unstable active regions releases stored magnetic energy as radiation, particle acceleration, and plasma ejections. The process is well characterized, mathematically modeled, and consistent with decades of observation. We know that AR4274 possessed a beta-gamma-delta magnetic configuration, one of the most flare-productive arrangements possible, and that such regions will eventually erupt based purely on their internal evolution. No external trigger is required by current models. We know that comets, when passing near the Sun, release plasma and can create localized heliospheric disturbances. We know that interstellar comets like 3I Atlas carry compositional and potentially magnetic signatures from their formation environments outside our solar system, making them fundamentally different from native solar system comets. We know that the heliosphere is a magnetically connected environment where disturbances can propagate along field lines across vast distances. What we don't know is whether any physical connection exists between 3I Atlas's perihelion passage and the November 11th flare. We don't know if the 13-day timing gap represents coincidence or correlation. We don't know if cometary plasma disturbances can propagate back to the solar corona with sufficient energy or appropriate characteristics to influence magnetic reconnection timing in active regions. We don't know whether interstellar objects with their foreign magnetic and plasma properties interact with heliospheric dynamics differently than native objects in ways that could affect solar behavior. We don't know because we lack sufficient data. 3 confirmed interstellar objects, 1I/Oumuamua, 2I/Borisov, and 3I Atlas, is not a statistically meaningful sample. We can't perform correlation studies, test hypotheses with multiple observations, or rule out coincidence based on 3 data points spanning half a decade. We're still in the early phase of interstellar object detection, where every new discovery adds fundamental information, but also raises more questions than it answers. The scientific consensus, as we've explored, doesn't support a causal connection. Experts who specialize in solar physics see no compelling evidence that comets affect flare dynamics, and the energetic and spatial scales argue powerfully against significant influence. This consensus deserves respect because it's built on expertise, mathematical rigor, and comprehensive observation of solar phenomena over many solar cycles. Dismissing expert judgment without extraordinary evidence isn't skepticism, it's arrogance. Yet science also advances by investigating anomalies, by asking whether edge cases might reveal phenomena that bulk statistics miss. The November 2025 timing is anomalous enough to justify careful attention, not because it proves anything, but because it suggests directions for future investigation. If we continue detecting interstellar comets at a rate of roughly 1 per year or 2, we'll accumulate more perihelion passages. If multiple future passages coincide temporally with major solar flares beyond chance expectation, that pattern would demand serious theoretical attention and drive research into mechanisms we currently dismiss as implausible. What's next then? First, continued monitoring solar cycle 25 will reach maximum activity around 2025 to 2026, meaning we're in prime time for observing major flares. Every active region, every eruption, every geomagnetic storm adds to the baseline against which anomalies can be identified. Space weather forecasting agencies maintain around-the-clock watch, and their data streams feed both operational decisions and long-term research. Second, improved interstellar object detection. The Vera Rubin Observatory, scheduled to begin operations soon if not already active, will revolutionize our ability to detect transient and moving objects, including interstellar visitors. More detections mean better statistics, clearer understanding of interstellar object properties, and more opportunities to study their interactions with the heliosphere. If the timing coincidence we've explored turns out to be repeatable, future observations will reveal it. Third, enhanced heliospheric monitoring. The Parker Solar Probe and Solar Orbiter missions are providing unprecedented close-up observations of solar corona and inner heliosphere. These spacecraft observe phenomena that Earth-based instruments miss, tracking magnetic field evolution, plasma dynamics, and wave propagation with high temporal and spatial resolution. If cometary disturbances do propagate sunward with physical significance, these missions might detect signatures we haven't yet recognized. Fourth, theoretical development. Even in the absence of strong observational evidence, exploring edge case mechanisms keeps theoretical tools sharp and occasionally reveals unexpected physics. Researchers working on magnetohydrodynamic turbulence, heliospheric current systems, and coronal dynamics might find that investigating cometary interaction scenarios, however unlikely, provides insights applicable to more mainstream questions. But here's what matters most for you, the person who's stayed with this investigation through 10,000 words of careful analysis. What you do with this information determines whether it remains isolated curiosity or becomes part of a broader cultural shift towards scientifically grounded skepticism and investigation. The comment section below is where this conversation continues. Share your perspective. Do you find the temporal correlation between 3I Atlas and the November 11th flare compelling, or does it strike you as coincidence inflated by pattern-seeking bias? Have you encountered other examples of astronomical timing that seem too precise to dismiss comfortably? Are there aspects of space weather and solar dynamics that this video hasn't addressed, but that deepen the mystery or alternatively resolve it? Your contributions matter because they challenge assumptions, introduce new perspectives, and sometimes point toward evidence or arguments that professional researchers might overlook. If you're hungry for more deep investigations into space phenomena that blur the line between established science and speculative inquiry, this channel is building a library of such content. Subscribe and enable notifications because the universe doesn't pause its mysteries for convenient upload schedules. The next interstellar object, the next major solar flare, the next unexplained correlation might emerge tomorrow, and rapid analysis while data is fresh provides value that retrospective studies can't match. Share this video with people who appreciate intellectually rigorous content that doesn't shy away from hard questions. In an online environment increasingly dominated by soundbite superficiality and algorithmic preference for outrage over insight, long-form investigative content survives only through community support. Every share extends reach. Every comment signals to platforms that thoughtful discussion deserves visibility. Every like tells the algorithm that depth matters. What we've explored here isn't conspiracy theory. It's not cherry-picked evidence supporting predetermined conclusions. It's honest examination of an astronomical coincidence that might mean something or might mean nothing, presented with full acknowledgement of mainstream scientific perspectives and limitations of current data. This is what responsible investigation looks like, distinguishing between what we know, what we suspect, and what we merely speculate about. The November 2025 event will be studied for years by solar physicists seeking to understand why AR-4274 produced such a powerful eruption when it did. The data from that flare and its associated coronal mass ejection will feed models, test theories, and improve prediction algorithms. Whether 3I Atlas played any role will likely remain unanswered unless future observations provide statistical weight currently lacking. But the question itself, the willingness to ask whether cosmic visitors from interstellar space might influence solar behavior in ways we haven't anticipated, that question represents healthy scientific curiosity. It embodies the principle that our current understanding, however sophisticated, remains incomplete. The universe is vast, complex, and interconnected in ways we're still discovering. Maintaining humility about the limits of our knowledge isn't weakness. It's the foundation on which future discoveries are built. So as we close this investigation, recognize that closure isn't the goal. The goal is informed curiosity, the ability to hold questions without demanding premature answers, the discipline to distinguish between evidence and speculation, while remaining open to possibilities that current consensus hasn't validated. That's the mindset that drives science forward, and it's the mindset this community values. The case of 3I Atlas and the November 11th, 2025 solar flare remains open. The evidence neither confirms nor fully dismisses the possibility of connection. The timeline intrigues, the physics constrains, the experts remain largely skeptical, and the universe, indifferent to our need for tidy conclusions, continues its complex dance of magnetic fields, plasma streams and objects wandering through the void, carrying secrets we're only beginning to read. Stay curious, stay skeptical, stay engaged, because the next cosmic mystery might be unfolding right now, waiting for minds sharp enough to notice the patterns and brave enough to ask the questions no one else is asking. That's what this journey has been about, and that's what the journey ahead holds. The investigation continues, with or without definitive answers, because understanding the universe doesn't require certainty. It only requires commitment to following evidence wherever it leads, and courage to explore the edges where mystery and knowledge collide.